Have you ever been on a plane and just looked out at the wing, wondering how we know for sure that it won't just snap off? Or how a bridge can stand firm day after day under tons of traffic? Well, it all comes down to one of the biggest and, frankly, toughest challenges in all of engineering, trying to predict when things are going to break. I mean, really think about it. That question is literally holding our modern world together. From these giant steel skeletons that make up our cities, all the way down to the microscopic little solder joints inside your phone, we're placing a huge amount of trust in materials. But, that trust isn't blind. It's actually built on a science that's dedicated to understanding a kind of invisible enemy. And that enemy has a name: material fatigue. The idea itself is actually pretty simple to grasp. Just like that paperclip, materials get tired. They get weaker when you put them under stress over and over and over again, even if that stress is way below what it would take to break them in one single go. The real trick, the billion-dollar question, isn't knowing that it happens. It's predicting exactly when. For decades, scientists have been on this epic quest to build basically a crystal ball for materials, a perfect model that could tell us the precise lifespan of any part, under any conditions you can imagine. But as it turns out, reality is, well, it's a whole lot messier than a nice, clean lab. Because when you get out into the real world, chaos is pretty much the new normal. The forces that act on materials out there, they don't play by our neat little rules. And that wild unpredictability is the #1 reason our predictive models so often fall short. And right here, this is the heart of the problem, the huge gap between the lab and the real world. In a test, we can apply a nice, smooth, repeating force. It's clean, it's predictable, it's easy. But reality? An airplane wing gets hit with sudden turbulence, a car suspension slams into a random pothole. The forces are all over the map. Engineers call this variable amplitude loading. And let me tell you, it is a complete nightmare to model accurately. And it's not just that the forces are random. As researchers Fiedler and Vormwald have pointed out, there's a whole bunch of other factors that just make everything more complicated. For instance, the order that loads get applied. It really matters. A huge impact followed by tiny vibrations is a totally different story than the other way around. And get this, the material itself actually changes over time. It can get harder or sometimes even softer. It's this process called cyclic hardening and softening. It's almost like the material remembers its own history, which makes trying to predict its future incredibly hard. And don't just take my word for it. As expert J.C. Newman puts it, this isn't some tiny little detail we're missing. It's a massive, fundamental challenge at the very core of this whole field. Even our absolute best models struggle with the pure complexity of reality. But here's the kicker. The external forces, they're only half the story. To really get what's going on with fatigue, we have to go deeper. We have to look into this hidden world inside the material itself. Because in there, these invisible ghosts are playing their own part in the whole drama. Yeah, because sometimes a material is already fighting a battle from within before it has ever faced a single force from the outside world. We're talking about two main culprits here. First, something called residual stresses. These are basically hidden tensions that get locked inside when an object is made. And second, it's microstructure, which is like the unique internal map of grains and boundaries that makes up the material. So let's talk about these residual stresses for a second. Research from folks like El Sharif points to welding as a perfect example. The incredible heat from welding leaves behind these locked-in stresses in the steel. Now, depending on whether those hidden stresses are trying to pull the material apart or squeeze it together, they can either create an easy superhighway for a crack to travel down, or they can act like a powerful roadblock stopping it in its tracks. It's this invisible variable that can totally change the game. Now, that second ghost, the microstructure, that's a whole different kind of challenge. See, a material isn't just one solid, uniform block. Research from Junjas and others shows it's this incredibly complex landscape of tiny little crystals, or grains. So when a tiny microscopic crack gets started, it doesn't just zip along in a nice straight line. Oh no, it has to navigate this maze, constantly getting blocked and forced to take detours by these grain boundaries. The specific winding path it takes is what determines how fast it grows, and predicting that path is, you guessed it, unbelievably complex. So you've got all this chaos on the outside, all these ghosts on the inside. Where do we even turn? Well, just like in so many other fields, researchers are now looking to a powerful new tool, hoping it can finally crack the code. That's right, artificial intelligence. The big idea here is that AI, with its incredible ability to crunch massive amounts of data and spot patterns that we humans would never see, could maybe, just maybe, build those perfect predictive models we've been dreaming of for so long. But it's not quite that simple. Turns out, AI has some pretty significant blind spots of its own. Research from Braun, Kellner, Molsky, and Tarasiuk
really highlights three major issues. First, AI is just insanely data hungry, and getting the kind of high-quality lab data it needs is really expensive and pretty rare. Second, there's the black box problem. It might spit out the right answer, but it often can't tell us why that's the right answer. And finally, a model that's trained on one specific material usually has a really hard time applying what it's learned to a different one.
So it's pretty clear AI is both this amazing new tool and also kind of a Pandora's box. On one hand, it has this incredible power to model complexity and make our predictions more accurate. But on the other, it's so dependent on data. And this black box issue means it's a very promising assistant, but it's definitely not a magic bullet. We can't just hand the whole problem over to the machines just yet.
Which means, of course, that the quest goes on. And scientists are pushing into even more extreme environments, tackling the final frontiers where predicting fatigue is more critical and way more difficult than ever before.
And we're talking about some seriously specific high-stakes challenges now, like trying to figure out how the tiny little solder joints in 3D computer chips can handle these intense cycles of heating up and cooling down, or predicting how unique magnesium alloys, the kind used to make cars lighter, behave where weird effects like twinning can suddenly make cracks grow way faster. Every single new material, every new extreme environment presents a completely new puzzle to solve.
So the big takeaway from all this research is pretty clear. Even after decades of work and with powerful new tools like AI, the Holy Grail, a single, unified model that can reliably predict failure for any material in any situation, well, that still remains just out of reach. The puzzle is very much unfinished. And that leaves us with a pretty deep final thought. Everything we build, taller skyscrapers, faster jets, more powerful electronics, it all pushes our materials right to their absolute limits. So as our technological ambitions keep soaring higher and higher, this whole quest to understand and predict failure, it stops being just an academic exercise. It's really about making sure the very foundation of our future is strong enough to support our dreams.